Okay, so I think we can start little by little. Good afternoon, everyone. We start our weekly seminar today with a talk presented by Alexander Shugurov from Nizhny Novgorod from Lobachevsky University. And this talk is presented as a part of a PhD studies, and the talk will be devoted to non-collinear electro-optic sampling of terahertz waves by ultra-short laser pulses in centimeter thick crystals. And this work was done at the chair of general physics of Lobachevsky University under the supervision of Mikhail Ivanovich Bakunov. So please, Alexander, I think you can start. We're looking forward for your talk.
Thanks. Hello, dear colleagues. Today I would like to talk about results of my dissertation work. Electro-optic sampling is a method which allows us to detect terahertz radiations electric field. In this method, probe pulse and terahertz pulse interact in electro-optic crystal. So due to Pokel's effect, polarization of probe pulse changed from linear to elliptical. These polarization changes could be measured by standard scheme consisting quarter lambda wave plate, Wollaston prism, and balance detector. Electro-optic sampling signal measured in this scheme is proportional to the terahertz electric field. Measuring changing the dependence changing time delay between terahertz pulse and probe pulse, we could measure the terahertz field in different times and restore the terahertz waveform. This method was experimentally demonstrated in an article of Q and X Junk in the scheme probe optical pulse with wavelengths around 800 nanometers interact with terahertz pulse in zinc fluoride crystal. In such crystal, for this wavelength, group optic velocity is equal to terahertz phase velocity. So optic pulse co-propagate with terahertz pulse, interact with terahertz field with one phase. But unfortunately, this situation could be fulfilled in only specific crystal for on specific wavelengths. For example, for 1.55 micrometers probe pulse, we couldn't find any such electro-optic crystal. So in this crystal, this question not fulfilled. So probe pulse move along terahertz pulse, interact with parts with different polarization, and result of electro-optic sampling will be distorted. In this crystal, we could define the coherence length. In this length, probe pulse and terahertz pulse propagates synchronously. And if we used the crystal length more than coherence length, the result will be distorted. So, for example, gallium arsenide for probe pulse with wavelength 1.55 micrometers should be used with a thickness around 1 millimeters. In such thin crystal, terahertz pulse sorry, forgot. So in this crystal, terahertz pulse originate echo signals, and if we measured echo signals with electro-optic signal, the result will be distorted, and we should filter out these echo signals. To filter out, we could use the time window of detection around several picosecond, but this what is echo signal? Echo signal is originate because of reflection of Terahertz pulse from the border of the crystal. If the reflected Terahertz signal interacts with optic signal, it will be measured too. And if we measured original and this signal, the result signal will be changed.
Why it is what is special in this signal? How does it? What is the physicals of this reflectance?
The physical reflections, no, Terahertz reflect from the border of the crystal.
Why
Like-
does it called echo signal? Is it something special or just usual reflected signal?
It's just usual Terahertz signal came to the this border, reflect on this border, and when we change the delay between optic Terahertz, optic signal can interact with a Terahertz signal, reflect Terahertz signal. Okay.
Alexander, what is the duration of terahertz pulse and probe pulse?
Probe pulse duration is around 100 femtosecond, depends of using lasers. Terahertz pulse around 5 or 7 picosecond.
So if I understand right, that the terahertz signal goes, then reflects from the border, goes back, and may again interact with the probe pulse, right?
Yes, we changed delay between pulses to measure the Terahertz fields in different parts. So if delay between the pulses will be
Long enough, yeah.
longer, yes, they could interact with reflected Terahertz signal.
So you see this time difference between between the terahertz and probe pulse, and then you might detune for a long time, but then you might start to interact with the reflected one, right? Also.
Right.
Okay. Okay. And this group velocity condition, so this basically some kind of phase matching condition. Yeah, it's you wanted to have to get efficient interaction between probe pulse and terahertz pulse, right?
Yes, yes.
Okay, okay, I got it.
Okay. So to filter out echo signal, we could use the small time window, but small time window means small spectral resolution of the detected signal. To overcome this problem, Mashkovich Tani and his scientific group proposed Noncollinear electro-optic sample method. In this method, probe pulse interact with propagate to Terahertz pulse at the Cherenkov angle. So projection of optic group velocity on the direction of Terahertz propagation is equal to Terahertz phase velocity. So we have synchronous propagation in this direction. In this shim, coherence length could be rewrite in this formula. So changing angle beta, we could change coherence length. It could be increased to around 1 centimeter, and using crystal with thickness centimeter allow one to increase time window, so increase spectral resolution, and increase interaction length, so increased efficiency of the detection. Efficiency of the detection, it's dynamic range of the detection. Okay. Sorry. Main purpose of my dissertation is develop method of noncollinear electro-optic sampling of Terahertz pulse by optical probe pulse in centimeter C crystal, which can provide efficient Terahertz detection with spectral resolution around something gigahertz. My dissertation work have introduction, 3 chapters, conclusion, reference links, and
yeah, Alexander, maybe can you get back to the previous slide? So probably the question is that so what is the problem you're dealing with, because it's very similar to so what's your next step? Will you discuss what's the next step comparing to the previous experiment you showed on the previous slide, right, in non-collinear geometry?
No, I think to set up as I understand well, you ask about problems of the noncollinear geometry.
So what we will be discussing what your work is, what is new in your work comparing to this one.
What new is my work? Yes. So I think I should.
Yeah, maybe you will cover it during the this talk. So
okay.
Let's go on. So sorry for interrupting. Yeah, go on.
Okay. I would say about quite later. So, as I said, my dissertation have introduction, 3 chapters, conclusion, reference list, and publication list. First chapter named Noncollinear electro-optic sampling of Terahertz wave in thick gallium arsenide crystal. Masashika Tani and his colleagues experimentally demonstrate noncollinear electro-optic sampling in lithium niobate crystal. This crystal have the high electro-optic coefficient, and this crystal is universal for different detection scheme because of refractive index of lithium niobate crystal is not depends on optic pulse wavelengths in diapason from 800 nanometers to 1.5 micrometers. So lithium niobate could be used as universal crystal for different detection system. Unfortunately, lithium niobate have Cherenkov angle around 63 degrees. So to enter the Terahertz pulse inside lithium niobate, one should use some coupling optic like silicon prism. Another problem of lithium niobate crystal is that it's inter-baryoff regions of the crystal. So different parts of optical pulse with different polarization divide in time in this crystal, and to compensate this effect, one should use additional polarization optic like in this shim to compensate this effect, which complicates this scheme. Unlike this shim, we used the gallium arsenide crystal. This crystal has Cherenkov angle around 12 degrees, so we have no necessity to use coupling optic, and this is isotropic crystal, so we have no necessity to use additional polarization optic to compensate baryoff regions. Before my answer about question of what I change in my research.
Any questions? No.
No. Okay.
No.
Before making an experiment, we analyze some factors that affect on electro-optic sampling. First of all, we calculate coherence length in gallium arsenide crystal. As you can see, using incident angle around 50 degrees allows one to achieve coherence length more than 1 centimeter for bandwidths from 0 to around 2 terahertz. After that, we calculate absorption length where Terahertz pulse decreased E times, and as we can see, this length exceed 1 centimeter in this bandwidth. Another problem that could be is dispersion bordering of the probe pulse. For the femtosecond probe pulse, dispersion bordering became sufficient in the distance more than 1 centimeter, either centimeter and 2 and 20 millimeters. So it could be it's not sufficient in our experiment. Noncollinear electro-optic sampling have another two problems. First of all, the probe beam and Terahertz beam. Probe beam crossing the Terahertz beam. So in the lens which we name cross lens, probe beam and Terahertz beam will be spatially separated. Another problem is that the different part of optical Terahertz, optical pulse could interact with Terahertz with different phases. So if different parts interact with Terahertz with opposite phases, we couldn't measure this frequency. We calculate the cut frequency, the maximum frequency we could detect, and this frequency was above 2 terahertz, around 2 terahertz. Crossing length was around 1.2 centimeters. We understand that perfect detection will be using probe beam incident on the lithium arsenide gallium with angle 50 degrees. Thickness of gallium arsenide should be around 1.2 centimeters. So we construct our experimental setup. In this experimental setup, we used fiber laser to pump a photoconductive antenna. Also, this fiber lasers was used as source of probe pulse. Both of these Terahertz and probe pulse focused on gallium arsenide crystal, and polarization changes measured by a standard scheme about I mentioned on the first slide. Here is results of our detection. We compared collinear electro-optic scheme and non-collinear electro-optic scheme in crystal with thickness around 1 centimeters and 1 millimeters. As we can see, the spectrum measured with non-collinear electro-optic scheme, with collinear electro-optic scheme in 1 centimeter gallium arsenide crystal is rather distorted because of coherence length is less than interaction length in this crystal. Compare the non-collinear electro-optic sampling in 1 centimeter thicker with collinear electro-optic sampling in 1 millimeter thicker. We could see that non-collinear electro-optic sampling have efficiency an order of magnitude higher than in collinear sampling. Also, we could see that spectral resolution in 1 centimeter crystal in non-collinear sampling is around 3 gigahertz, while the spectral resolution in collinear electro-optic sampling in 1 millimeter crystal is around 40 gigahertz. After that, we investigate dependence of the spectrum of crystal thickness. As we can see, crystal with thickness 4 millimeters measured signal from the crystal with thickness 4 millimeters have low efficiency. Question?
There is a question in the chat, but maybe yeah. How was the spectrum on the previous slide obtained? So for this one, previous slide. So how did you obtain the spectrum?
So obtain spectrum. We measured electro-optic signal from the different schemes. we measured electro-optic signal from non-collinear electro-optic sampling, black curve, from collinear electro-optic sample in centimeter crystal, and collinear electro-optic sample in millimeter crystal. After that, we made Fourier transform of the electro-optic signal and have these spectrums.
Sorry, can I ask some more questions about that?
Okay.
Yeah. Okay, so basically the question is, so you're measuring only the probe pulses here. So basically,
sorry?
so you are measuring only probe pulses, yes? So
yes, we measured polarization change of probe pulse.
Polarization change. Okay, so by using so as far as I understand, yeah, you by varying the time delay between probe and pump pulses, yeah, and using so you basically measure the spectrum in time domain. Is it correct?
Yes, typical results is signals like that. So we measured amplitude of terahertz field in different times and restore the terahertz waveform. After that, we take Fourier transform and have the spectrum.
Okay, so the resulting spectra is the Fourier transform of time domain measurement of delay between of this polarization change, which depends on the delay between pump and probe pulse. Is that correct?
Yes.
Okay, this is important. Yeah, and this is very important because it's the technique is not that obvious. Okay, thank you.
Okay. Sorry. Okay. This in the slide we measured spectrums of terahertz pulse of electro-optic signal with dependence of crystal thickness. As we can see, the spectrum obtained by using crystal with 4 millimeters thickness. This efficiency of this measurement is lower than another two, than obtained by using 1.3 centimeter thickness and 2.7 centimeter thickness. It could be explained the fact that in this crystal interaction length will be limited the crystal size, not the crossing length between probe and terahertz pulse. In another two signal spectrums, the interaction length limited by crossing length, but using crystal with but more thicker crystal allow us to increase terahertz or to increase the spectrum resolution of the detector against pulse. Finally, we measured dependence of electro-optic signal from the incident angle on the crystal. As we can see, spectrum obtained by using 42 degrees and 50 degrees incident angle is almost the same. In this time, spectrum obtained by using 33 degrees is on high terahertz is less than another two. It could be explained. Question?
No, yeah, please finish the sentence.
Okay. It could be explained the fact that coherence lengths for this angle on high frequencies are lower than the interaction distance. So main result of this chapter is that noncollinear electro-optic sample that we proposed and experimentally demonstrate noncollinear electro-optic sampling of terahertz pulse using femtosecond fiber lasers. The efficiency of electro-optic sampling are an order of magnitude higher than efficiency of collinear electro-optic sampling, and spectral resolution is around several gigahertz instead of several around 40 gigahertz. Question?
Alexander, yeah, can I ask from the previous slide a question? Yeah.
Okay.
So here, do I understand right that 42 degrees is kind of an optimal angle of interaction because intensity is higher.
Yes, but intensity is not very higher. In other work, we used incident angle around 45 degrees. So in our article, we make a conclusion that optimal angle is between 42 and 50 degrees. So if we look in this, we could say that 42 degrees coherence length on 2 terahertz is less than 5 millimeters. So it's low limit of optimal detection.
Okay, thank you.
Okay. Next chapter named Nonellipsometric electro-optic sampling of TraGaAs wave in
Alexander, sorry for interrupting. Can I ask one more question about the first chapter, please?
Okay.
Can you please repeat? Probably I just missed. So basically, the idea of this method, is it to measure the spectrum or to somehow characterize the change in polarization of the propulse?
In this method, we measured polarization changes of propulse. In electro-optic crystal, due to Pokel's effect, the propulse changed from linear to elliptic. So these polarization changes could be measured by this scheme. Not a question.
Okay. And how the obtained spectrum actually characterize these changes? So you in the end of the chapter you showed the spectrum, yeah, but how?
Yeah. This polarization changes is proportional to Terahertz field.
Okay.
Okay.
So basically the idea is to so the idea is to pump the crystal on different frequencies as much as possible to obtain this high changes in polarization. Yes.
Sorry, I miss you.
Okay, can you please repeat the information about the spectrum on the last slide? So basically, what does it mean? So why do we need here high intensity?
High intensity?
Or yes.
High intensity means high dynamic range, and it detects could you explain? You mean? Can you repeat the question?
Okay, so what is the meaning of spectrum here? How does it?
What is the meaning of spectrum?
The experiment, yes.
Spectrum. We used some trigger source, and we measured this source by different. We measured targets originated from the source with different methods. As high we see signal, we not need the high signal, we need the high dynamic range between signal and the noises. And as all signal was numerated to noises, and if the signal is higher than another, it means that in this method, the signal to noise ratio is higher than in another method.
Okay. So we're trying to get as high signal on every frequency as possible here, or what, or we characterize the TraGaAs pulse somehow.
No, we measure as high as possible.
Okay. Thank you. Let's go further. Okay, thanks.
Okay. The second chapter. Another method of noncollinear electro-optic sampling was proposed by Masashika Tani. In this method, named heterodyne electro-optic sampling or nonellipsometric electro-optic sampling, the GaAs and pulse and optic pulse interact in lithium niobate crystal, and after this interaction, optic pulse have amplitude modulation, which could be measured by signal photodetector. So we could measure the Terahertz pulse or Terahertz field without using any polarization optic at all. So standard scheme means quarter length wavelength and Wolfson prism, but this scheme there is no polarization optic. We measured by only a photodetector. The theory of this method was proposed in the article of Mikhailovich Bakunov, and according to this theory, this amplitude modulation originate by the process of generation of some frequency and different frequency generation. And due to this process, the probe pulse has amplitude changes in different paths. If we used collinear electro-optic sampling, this amplitude changes compensate each other, but in non-collinear, they could be divided. In this method, electro-optic sampling signal is proportional to imagined part of Terahertz field, multiple on the transfer function. About this function, I will talk a little bit later.
Alexander, but what do you measure here by sampling? You measure the intensity of some frequency or what?
Measured of electro-optic signal. So, like in previous method, optic propagate with Terahertz pulse, changes amplitude because of Terahertz field, changing the time delay between optic and Terahertz pulse. We could measure field in different times.
Okay, I got it.
So this method, like that method, it's also electro-optic method, but we measured not polarization change, we measured amplitude change. Okay. Instead of scheme of Masashika Tani, we used gallium arsenide crystal. We construct our electro-optic sampling setup, which could work in two regimes. Regimes of ellipsometric sampling and non-ellipsometric sampling. Regime of ellipsometric sampling is copy the scheme which was used in a previous chapter. In non-ellipsometric scheme, D-shaped mirror used to divide pulse on two halves. That's directed on balanced detector. Switching between these regimes, we could switch between these regimes by using flipped mirror and rotate the gallium arsenide crystal. Axis 001 in ellipsometric mode should be aligned along optical electric field of optic signal, and in non-ellipsometric mode 001 axis should be aligned along electric field of Terahertz pulse. Here you can see our results. We measured several signals for different probe beam widths, and also we measured ellipsometric signal, like in previous chapter. As we can see, the efficiency of this method is the same order of magnitude. as we can see in spectrum, the non-ellipsometric scheme works as band-pass filter. So if you used 80 micrometers probe beam width, the low frequency is suppressed and but we can detect high frequency. If we used 500 micrometers probe beam, the high frequencies are filtered out. To explain these results, we consider the theory which was obtained in this article. According to the theory, transfer function H is defined by probe beam width. So it depends of omega c, which depends of probe beam width. We calculate the transfer function for different probe beams. As we can see, for probe beams with width 80 microns, the optimal detectable frequency is more than 1 terahertz. For another frequencies, the optimal detectable frequency is less than 1 terahertz. Also, we could see that for low frequencies, transfer function for 80 micrometers probe beam, on low frequencies, this transfer function is can be we can think that it's linear. It's linear. If we change the transfer function as omega, it could be seen that the textual electro-optic signal will be looks like time derivative from the signal measured by electro-optic sampling scheme, ellipsometric sampling scheme. So the result of the chapter that we demonstrate noncollinear electro-optic sampling in gallium arsenide crystal. Efficiently of noncollinear ellipsometric and non-ellipsometric sampling are comparable, and non-ellipsometric electro-optic sampling operates as a bandpass filter. Questions in the chapter? Oh, okay. So chapter. Noncollinear electro-optic sampling of Terahertz wave in lithium niobate crystal while avoiding the effect of instant birefringence. In the scheme, which was used by Masashika Tani, used gallium lithium niobate crystal with which optic axis was orthogonal to the direction of propagation of probe pulse. In this configuration, the lithium niobate, the part of probe pulse with different polarization will propagate like ordinary and extraordinary wave. So they have different velocities, so they will be divided in time, and we couldn't measure them. This configuration have advantages about the highest electro-optic coefficient, but unlike this, in our work we obtained detection scheme, a proposed detection scheme in which probe optical pulse propagates along the optic axis. In this regime, the different parts of optical pulse with different polarization propagates as an ordinary wave, so they have equal velocities, so we could detect our results without using any additional optic to compensate birefringence. Unfortunately, we lost in Terahertz electro-optic coefficient, but as we show later, we still could make efficient measurement in this crystal.
Alexander, I have a question here. So what are the expected delays on the sizes of your sample between two polarizations in case of birefringence? So is it a real problem, or maybe it's
they almost divide each other, divide each other. So in quarter lambda wave plate, we have not elliptic polarization. We have two different linear polarization, this and this. Both of them make round polarization, so balance detector not measured any signal at all.
I see. So the difference is large.
Yes, well large. As I can see earlier, the refractive index of lithium niobate crystal is almost independent of optical probe pulse wavelengths in diapason from 0.8 microns to 1.55 microns. We also calculate prism apex angle and see that this angle also the same. So we could use the system of silicon prism and lithium niobate in difference in experimental shim, which use different lasers which use different lasers. To illustrate this, we make two experimental setups. First experimental setup used fiber laser with wavelength 1.55 micrometers. This experimental setup is almost that in previous chapters. Instead of using lithium niobate crystal and silicon prism, instead of gallium arsenide, and here presents iris diaphragm. This diaphragm is necessary to cut only that part of probe pulse that propagates near the border between lithium niobate and silicon prism. We cut this pulse, this part, because of Terahertz in lithium niobate. Lithium niobate absorbed Terahertz pulse, so we need only we need interaction area which lies only near the border. So experimental setup for titan sapphire lasers. In this experimental setup, we used another lithium niobate crystal with special silicon prism, which allows one to radiate Terahertz pulses collinear to the pump pulse. In this experimental setup, the same crystal as in this experimental setup is used. So this is the result of our experimental setup in our first experimental setup. As we can see, efficiency of the detection with lithium niobate crystal is the same order like with photoconductive antenna and for noncollinear electro-optic sampling in gallium arsenide crystal. The result of our experimental second experimental setup in this slide. So we could see that we could make efficient electro-optic detection in both shim. So the lithium niobate with silicon prism could be used with different experimental setups with different detection schemes. The main result of the chapter that noncollinear electro-optic sampling was experimental demonstrate and proposed and demonstrate the efficiency of electro-optic sampling with photoconductive antenna electro-optic sampling in gallium arsenide crystal and proposed methods are almost the same. And the spectral resolution in this method is around 10 gigahertz. Thanks for attention.
Thank you, Alexander, for a very inspiring and interesting talk. So I welcome question from Zoom, but while people are preparing, I have a question, maybe a very general one. So lithium niobate and gallium arsenide, so they have quite different values of nonlinear coefficients, if I remember it right.
Yes.
Yeah, so gallium arsenide should be much more strong nonlinear optical material. But you say that the efficiency are comparable. Why does it happen? So if I remember right, there's almost 10 times difference or 5 times difference in nonlinear.
Yes, as I said in this scheme, we used not the highest electro-optic coefficient of niobate lithium. We use another coefficient, R22. It's not higher than in gallium arsenide, not so higher.
Okay. Okay, so you don't have the values right here. But okay, yeah, all right, so it's not the most. But is it possible to use a more efficient geometry?
Sorry?
Is it possible to use more efficient geometry?
Yeah, more efficient geometry. No, I think maybe yes, in some other crystal.
Mm-hmm. Okay.
Nothing.
Any questions from Zoom? No. All right, maybe I will have another one, maybe not directly related to what you were showing today, which is very interesting, but you use fibers, yeah, so to let's say illuminate the system, but are there any approaches to do all the same in waveguides? So electro-optical sampling, but not in a free space, not in a bulk crystal, but let's say in a waveguide crystal. So just making a planar waveguide on top of the dielectric surface and doing that, let's say planar geometry.
So question is it workable in waveguides or?
Yes, exactly.
No, as I understand well, the Masashika Tani used waveguide of lithium niobate, not blank lithium niobate.
Yeah, but the interaction with so they were exciting the femtosecond pulse was propagating in the waveguide, right?
Yeah. As I remember, there was around about 50 or 20 micrometers. Forgot, sorry. No.
Like the thickness.
The thickness of niobate lithium.
Yeah, but it's not really a waveguide. I mean, a waveguide, I meant a few microns for like a single
waveguides.
I would say that probably maybe the interaction would be more efficient, or the spatial overlap will be small, I guess.
Так, and to enter the terahertz in this waveguides. So terahertz enter from this to the waveguide, and but I think in such thin crystals, the terahertz will reflect from this part, and some frequencies will be suppressed.
Mm-hmm. Yeah, maybe the efficiency will be not that high. Okay, thank you. So any more questions in Zoom, please?
Probably I can ask some like more experimental question. What is the most difficult thing then you would be in the experiment, and you're trying to achieve overlap of terahertz and optical pulses in this space domain on the prism?
Sorry, what is the most difficult part of?
Achieving the overlap of terahertz and optical pulses.
What is the difficult part of the experiment?
Yeah.
Yes. No, for in first two chapters it was quite simple experiments. This photoconductive antenna and probe pulse in free space. It was they propagate quite simple, and the geometry is quite simple. But in this experiment, the problem was with this diaphragm. It should place very a small mistake in placing this diaphragm changed the signal sufficiently. If this diaphragm will be if we drive this diaphragm to the lithium niobate, the high frequencies of terahertz will be suppressed. If we drive this diaphragm to the silicon, we couldn't measure the signal at all. So placing this diaphragm was the difficult thing in all experiments.
Okay, thank you.
Okay, if there are no questions, so I think we can thank the speaker again for a very beautiful talk, and I think this is it. So we can finish our today's seminar. We thank Alexander for staying with us today. Regarding the next seminars, follow for the updates. It will appear in our chats and in the mailing lists. Thank you very much to everyone.